Hi, everybody. There's about 30 of us here so far, but the numbers are still climbing, so we'll wait another minute or so for people to file in before we get started. Okay, we're starting to slow down. So I'm going to begin the introduction. We'll get Susan going in a moment. But first of all, I'd like to welcome all of you. Thank you for being here and joining us for this installment of the ISEA webinar series. We've got an exciting guest today, Susan Shull. She is not only the treasurer of ISEA, but she's also the founder and lead consultant of SOS Consulting. She has more than 30 years of experience in manufacturing, nonprofits, and higher education using engineering, statistical, and business process improvement methodologies, delivering over $250 million for clients. And today she's going to talk about a topic that stems from a paper she wrote in a recent special issue that Quality Engineering released on statistical engineering. So if you want to learn more about what Susan has to say today, the paper will be available or linked for you in the details of the webinar later on our website, and you can go there for more information if you'd like. But for now, we'll welcome Susan, and I'll mention just one more housekeeping item, that if you have questions throughout the presentation, there is a question feature in GoToWebinar that is separate from the chat feature. So if you have questions, type it in the question box, and I'll make sure they get answered at the end. Okay, with that said, thank you, Susan, for being here. We appreciate your time, and we all look forward to your talk. And feel free to go ahead when ready.
It's a pleasure. Thank you for inviting me. Good morning, good afternoon, good evening, whatever time zone you're all listening in on. I'm going to turn off my camera so you don't need to be distracted by my messy office behind me, and just show the slides here. I do want to take a moment of privilege, though, and recognize my grandfather, Charles H. Shull Sr. This was his birthday, June 8th. He was a coal miner and a carpenter with no more than an 8th grade education, but a masterful problem solver. We lived next door to him until I was 5, and I was his shadow, so I wanted to do everything that he did, which meant fixing things, anything from chairs to lawnmowers and washing machines and whatnot. He was always fixing something. And as a little girl, I never heard, no, you can't do this because you're a girl. Never once. He taught me how to use tools. He explained what he was doing and why he was doing it, and how to best use the resources that we had available. So I am in large part an engineer because of my grandfather. So thank you, Grandpa. I want to just honor him today. To the presentation, I have 3 objectives. One, to compare statistical engineering to established engineering disciplines and identify similarities. Share some personal experience integrating statistical engineering into my work throughout my career, and explore the potential of how statistical engineering can help solve some of the large unstructured challenges that face our planet. So let's start with a definition. What is engineering? Webster's defines it as the application of mathematical and scientific principles to practical ends, such as design, construction, operation of economical and efficient structures. So in other words, engineers invent, design, build, solve, and improve, or as I like to tell the 7th graders that I work with sometimes, engineers solve problems. So what is the problem? ABET, the Global Engineering Accreditation Organization, defines complex engineering problems as problems that include one or more of these characteristics, as wide-ranging or conflicting technical issues, no obvious solution, non-encompassed by current standards, regulations, or codes, involve diverse stakeholders, and has many parts, and it involves multiple disciplines that have a significant complex consequences and a wide range of contexts. Too many words there to get out of the mouth, excuse me. In other words, complex engineering problems are messy problems. Engineers have had a significant, profound impact on the world in which we live. Over the last 100 years, engineers have brought electricity, light, and energy across the world, influenced transportation, influenced our food and water supply, communications, healthcare. Just about everything that you touch and do today has had been influenced in some way by engineers. But just as there are many types of problems in the world, there are many types of engineering. And they can be classified into 7 categories: biological, chemical, civil, electrical, geotechnical, management, and mechanical. Examples of biological are biological, agricultural, biomedical. Examples of chemical, or in addition to chemical, materials, polymer engineers. Civil would be civil engineers, construction engineers, structural engineers. Electrical, beyond electrical and electronics, would be computer and software engineers. Geotechnical would include environmental, geological, mining, metallurgical engineers. Management engineers would go to engineering managers, industrial systems engineers. Mechanical would include nuclear and manufacturing, aerospace, in addition to mechanical engineers. So lots of different types of engineering depending on the type of problem. The general body of knowledge for engineering, as defined by the Engineering Accreditation Commission, consists of 4 major topical areas: college level mathematics and basic sciences. And those basic sciences primarily consist of chemistry and physics and other natural sciences. Then engineering sciences that are based on that mathematics and sciences but carry the knowledge further towards application. And lastly, engineering design, which is an iterative process of devising a system, a component, or a process to meet needs and specifications within constraints. The engineering criteria require a minimum of 30 credits of mathematics and basic sciences and a minimum of 45 credits of engineering science and engineering design. So anyone that has graduated from an ABET accredited engineering program has met those minimum educational requirements. Of course, the different disciplines have specific needs around what science and engineering sciences or what types of design you're focused on, and those are carried further in the specific criteria for each of those disciplines. The engineering design process, as I already mentioned, is an iterative process, and a simplified version of that process is shown here in this graphic. Starts with defining the problem. What is the problem and what are the constraints? And then imagining the solution, brainstorming ideas and what could solve that problem, and then choosing the best one that will address the constraints as well. Planning it, designing it in detail, doing the engineering drawings, identifying the sequence of steps and the materials that would be needed, and then following that plan, creating the solution, testing the solution, and finding ways to improve it, and repeating the cycle to continue to refine the design, refine the solution, so that it addresses not only the problem, but is well within the constraints in an effective and efficient manner. So given all that, then what is statistical engineering? ISEA, in our Statistical Engineering Handbook that is available to all members free on our website, defines statistical engineering as the study of, so it's not tools and methods, it's the study of systematic integration of statistical concepts, methods, and tools. So looking at the diagram on the right, it is that bridge between statistical thinking, statistical concepts, and the more operational statistical methods and tools. And it's often the integration with other disciplines, which we'll get to in the next slide, to solve important problems sustainably. And I want you to remember that last phrase, solve important problems sustainably. We will address that later in the presentation. So the integration with other disciplines, statistical engineering really integrates the other disciplines and the human element, team building, and integrating those other disciplines in a collaborative team environment to bring all of the tools that we each bring to the table, including the organizational and behavioral elements of people, to create better, faster solutions to these messy, complex problems that we face in our world. And the problem-solving process typically follows these 6 phases. Again, we identify the problem. We make sure we're focused on a problem and not a symptom. But what is defining that problem and providing structure to it? That is clarifying the mess, separating the signal from the noise, and understanding the broader context in which it resides, the history, the politics, the personalities, the stakeholders that are involved in this situation. And then develop a strategy on how we're going to attack that problem. What's the approach we're going to take? It is an iterative process. You notice the cycle that goes back to the beginning. So what's the sequence in which we're going to work through this process? And then the specific tactics of the alternatives and the tools that we will use, and try it out and test it, verify what works, what doesn't work, repeat the cycle to improve and refine the solution. So it's really bringing the statistical tools together with people and multiple disciplines to solve the problem in a broader context. Now, what's unique about this process is compared to the engineering design process are these 3 steps in the middle: providing structure, understanding context, and developing strategy. Clarifying that mess and understanding the broader context, as well as how we're going to work through this sequentially, are typically not well addressed in engineering problem solving. In fact, many of my peers jump from identifying the problem to a solution without considering the broader context and the people elements involved in it. Sad to say, but that's often what happens. So how does the engineering design process compare to the statistical engineering process? I think we could help our engineering peers slow down, go slow to go fast later in the beginning phases of the engineering design and problem solving process by understanding the context and developing that strategy. So taking a little bit more time in the engine phases of their design and problem solving processes. Statistical engineering has sort of a body of knowledge. These are not called as such in the statistical engineering handbook, but if you look at the table of contents, these are the major topical areas in the handbook that could be interpreted as a body of knowledge. Since I shared with you general body of knowledge for engineering, compare that to the body of knowledge with statistical engineering. The topics on the left are statistically oriented, things that you would see in a statistics program. The things on the right, however, are probably not. They are the more people, organizational, stakeholder types of topics: leadership, communication, teamwork and collaboration, change management, project management. So broader set of tools that incorporates multiple disciplines and stakeholders and people. So where then might statistical engineering fit in the 7 different categories of engineering? I propose that it would fit within the management category, and that, like industrial and systems engineers, it's looking at the integrated systems of people, materials, equipment, and energy to solve problems, and it is not specific to any of these other topical areas of biology, chemistry, structures, electricity, earth materials, or mechanical things. So my industrial engineering friends may say to me, well, okay, Susan, how is this different than industrial engineering? So I share with you here the 14 topics identified by the Institute of Industrial and Systems Engineers as the industrial engineering body of knowledge. And you will recognize here that these are topics that are much more industry oriented. The roots of industrial engineering are manufacturing. So to no surprise, you would expect to see topics that are much more oriented around manufacturing processes, work design, facilities engineering, safety management, those kinds of things. You will also notice that there is the potential for overlap in the tool set that we use, particularly in quality and reliability. The statistical tools come into play there, also in operations research, but many statistical tools come into play in work design and measurement, and in facilities design and supply chain management. So there is quite a bit of overlap, but we are two different disciplines. Share a little bit about some of my experience in integrating statistical engineering and industrial engineering. I've done this my entire career without recognizing it. In fact, I was doing it early in my career 40 years ago when I'd never heard of statistical engineering. And I just want to highlight a couple of things on this slide. I could easily spend an hour on each of the project examples that are here on the right. And since we don't have that kind of time today, I know you didn't sign up for an all afternoon webinar. So I'll just try and highlight some key points here. My very first project at Kodak was documenting offline product testing procedures. And perhaps another industrial engineer would have just documented them, worked with the technicians that were running them and gotten them down on paper, maybe with a few pictures or graphics to go along with them. But as I got into it, learned that many of these tests were designed for specific reasons to pick up or detect possible product defects or issues in the field. And that the sampling plans, the sampling size, and sample frequencies didn't have any statistical basis to them. They were just ad hoc, put in place by the technicians that had developed them to get some data to the product engineers, and had not incorporated any of the statistical aspects of that. So we updated and refined those procedures to include sampling plans and sampling frequency, and in some cases eliminate some of the tests because we found that they were no longer necessary or needed, that the new products had been developed or products had been improved, that those issues no longer existed. And we were able to, again, statistically prove that and eliminate some of those tests, or online tests had replaced them, and simplified that. In my DuPont experience, I worked on a corporate initiative that we called Continuous Flow Manufacturing, or CFM for short. It is essentially lean manufacturing. DuPont had worked in partnership with IBM on bringing this methodology into the corporation. It had a very distinct, discrete parts manufacturing orientation to it. And of course, DuPont was dealing with chemicals, things that flow. And the thing that was the aspects that were missing in that distinction were the variation in the chemistry and in the flow of materials through our manufacturing facilities, such that many of the bottlenecks we were seeing were due to that variation, and that had not been fully incorporated into the methodology that IBM had presented DuPont with. And so we incorporated, myself with some of my peers, incorporated the concepts of variation into CFM, including teaching the shop floor teams the Magnificent Seven quality tools, and some of the internal consultants that were helping to deploy this across the organization, tools like regression analysis and design of experiments, to better incorporate variation into the deployment of this methodology across DuPont's manufacturing facilities. I continued that experience in my consulting over the last 30 years. And two examples I have documented and have been published, so I cite them here for the sake of time. The first one, process variability reduction, took advantage of my experience with CFM at DuPont in working with a client that was seeking to reduce the variation in the throughput of the product through their facilities. And that was published in the first special issue on statistical engineering and quality engineering in 2012. You can see that reference there. Then I think it's quite commonly recognized as Six Sigma as statistical engineering. Sometimes in its deployment in some organizations, the leadership and the people elements are not fully incorporated. And so I have written an article in the Six Sigma Forum magazine on how to incorporate organizational health into your deployment of Six Sigma, and that reference is there on the slide as well. And then an example of incorporating engineering into statistical engineering, I was doing Six Sigma work with a large commercial bakery in Richmond, Virginia, where they made chocolate chip cookies. At least once a week, they experienced a batch that was too dry or too wet, and when it would go into the oven, the cookies would all burn, and so they'd have a whole batch that would be scrapped. And this was hundreds of cookies, so very expensive loss. And following the Six Sigma process, the measure phase, of course, we map out the process and we identify all of the inputs and the outputs for each step in the process. And through that work and prioritization of those inputs, as to no surprise, if you do any baking at home, the ingredients, the flour, the sugar, the oil, the water, the chips, all those things came up high on the list as potential factors for creating this problem. And so when we started to move into the analyze phase, I questioned them about obtaining access to this data, because the charging of the mixer with the ingredients was all done with an automated system. So operators were not physically measuring the flour and then dumping it into the mixer like you would do manually at home, but it was all being done through an automated system and a massive loop that they had that brought materials in from silos to each tank and batched them into the tank. And so I quizzed them about getting access to that data, and the engineer that was the greenbelt on this project said, doesn't exist. If it's an automated system, guys, it exists. All my engineering experience in chemical manufacturing says it exists, or you have the potential for it to exist. If it doesn't, then go back to the vendor that provided the system to you. We went weeks of, no, it doesn't exist, Susan. Finally, I went to the plant manager and said, humor me and prove to me that it does not exist. As I know you're using a Fisher control system. I know Fisher control systems have the capability, engineering-wise, to provide us with this data. So they finally, to prove Susan wrong, went and engaged the vendor that installed the system for them. And he said, yeah, the data's there. I just have to grant you access. And when they obtained that access, lo and behold, they not only had data for recent batches, but they had 7 years worth of data from that mixing process. They were overwhelmed with data, actually. So we had to focus it on more recent events and a recent time period to represent the quality of the raw materials and the vendors that they were currently using for those raw materials. And yes, ingredients, primarily flour, turned out to be a critical factor because they were such large batches, 750 pounds of flour. It's an enormous amount of flour. And their loop that moved this flour through the system and then waded into the mixers couldn't in one cycle dump the complete amount. So it had to go through multiple cycles before it provided the full quantity for a batch of these chocolate chip cookies. And that the amount and the number of times that it was added and the delay between them influenced the addition of other ingredients and the incorporation of other ingredients, such as the sugar and oil and water, into the process. So the programming around that addition of flour and management of that loop between multiple mixers had to be adjusted as a result of that. And again, incorporate engineering into that process, understanding the variation in the process and the impact that it had into mixing. We also discovered that oil, which was controlled by a separate system, was added into the mixer using a micromotion meter. Now, all the process control engineers that I know will tell you that micromotion meters are near the closest thing to being perfect that exists in terms of meters. And yeah, compared to the alternatives, they probably are, but they are not perfect. In fact, some of the engineers that I worked with at DuPont ran experiments and proved that under the right conditions, air would get into the system and you'd have periodically like a burp in which more would be added or less would be added to your system. And my bakery client did not fully want to accept somebody else's data. So I helped them design experiments again to recreate that in their situation. And we verified that, yes, given their meter and the ingredients that they were dealing with, that they could get air in the system that would result in these occasional burps in the micromotion meter and deliver too much oil or not enough oil, and that impacted the batch and could result in burnt cookies. So several examples and references to several others that you could see how statistical engineering and other engineering tools and concepts can be integrated together to solve problems, at least in manufacturing. But the world has bigger, larger challenges in front of us. In fact, in 2008, the National Academy of Engineering, so NAE, that's what that is in the title, National Academy of Engineering, identified 14 grand challenges of our planet. And I won't go into them in detail here. You can go to their website, which is linked on the bottom of this slide, and learn more about each of these. But they are all problems that will require multiple disciplines coming together and working collaboratively to solve these problems of our planet. I'd just like to talk about a couple that may be areas where we as statistical engineers can have an influence. Take, for instance, number 5, provide access to clean water. We in North America are very fortunate in that not only do we have easy access to clean water that we can drink and use for cooking purposes, but we bathe in drinkable water. Most of the rest of the world does not. And so they need access to clean water. And that may include understanding the context, going back to those 3 steps that are often missing, going back to the full context of the water situation. What are the communities and the peoples and the cultures in which where water exists and where water does not exist? Is now, if we're providing access between those 2 communities, we need to consider the impact of connecting these 2 communities and all of those stakeholders. We may also need to consider the quantity of water in the source and how it varies over time from season to season, year to year. So thinking of the stochastic nature of nature and the water quantity and choosing more robust sources and then means of connecting the people that need it to the source. Then also let's explore number 6, restore and improve urban infrastructure. Most of our infrastructure in our communities is 50 to 100 years old, and it is deteriorating, in some cases deteriorating quickly. Unfortunately, my civil engineering colleagues in their design of infrastructure tend to use tabulated values. So they view things as being deterministic, a single value in their design parameters, rather than understanding this, again, the stochastic nature of the environment in which this infrastructure will reside, and then the interaction of people with that infrastructure. So there's a couple of opportunities where we as statistical engineers may make a big impact to address some challenges. And I hope that you would be a voice along with me of us having a role in that, because I believe we can help provide better, faster solutions to these challenges. So in summary, statistical engineering is a lot like the established engineering disciplines in that it is focused on solving the messy problems of our world. And it uses a common process for solving problems that's quite common, quite similar to the engineering design process, but yet brings some unique additional viewpoints around the context of the problem that could aid those other engineering disciplines in their problem solving efforts, and hence help us provide better, faster solutions to the grand challenges that face our planet. Nathaniel, what questions do we have?
Well, first of all, I'll thank you on behalf of everyone here. That was an excellent presentation. There are some questions that I'll read to you, and I've got some of my own, but I'll just remind everybody who is here, if you have questions, now's the time to ask them. There is a question feature in GoToWebinar, so just type them in there and they'll pop up on my screen. And then I can ask
email
them.
me. My email address is here on the screen.
Yeah, and if we don't get through everything, feel free to follow up with Susan. I will emphasize again that the talk here was based on a paper of the same name in the special issue on statistical engineering, which was the 4th issue of Quality Engineering in 2022. So if you want to dig deeper into this or any of the other exciting papers from that special issue, you can find them on Quality Engineering. So that was the 4th issue in 2022. Okay, so I'll start with a question of my own. You earlier in the presentation listed the educational requirements of someone who studies engineering in an ABET accredited program, and we're not there yet with statistical engineering, but I wonder if you could just comment on your opinions or what you think of sort of the necessary training of a quote unquote statistical engineer, because there's a few follow-up questions here about I think, you know, who is a statistical engineer. So in anticipation of that, maybe you could talk a little bit about what you see as relevant
if you
training.
would have a statistical engineering program anywhere in the world, for that matter, that would wish to be accredited, be recognized by ABET as an accredited engineering program, then it would have to meet these requirements. I put that slide back up at a minimum. And then we, probably ISEA, as the society defining the body of knowledge, would define additional program criteria that defined the unique engineering sciences and design components, and perhaps the faculty requirements to teach the curriculum that would address the body of knowledge that we define as statistical engineering as we define it in the handbook. I don't want to preempt that with my own opinions. I think that is really something that we collaboratively need to define, and then probably need to collaborate with our closest peers, such as those in my discipline, the Institute of Industrial and Systems Engineers, in defining that. But at a minimum, it would need to meet these requirements. And then the program criteria, which I don't have here, are unique to each discipline. If you're interested, the ABET Engineering Accreditation Commission criteria, is available on the ABET website, which is abet.org. And one of the menu items has an option for finding the criteria. And there's a page of program criteria for every discipline that ABET accredits. And there are many of them, 30 pages or so of them. So I just chose to show you the general requirements that all engineering programs must meet as a minimum.
Okay, yeah, that's helpful. So then as a follow-up, maybe could you go to slide 11? or it shows the definition of
Yes.
statistical engineering.
Yes.
So I'll just read it again here. It's the study of systematic integration of statistical concepts, methods, and tools, often with other disciplines, to solve important problems sustainably. And so one of the nuances of this definition that was pointed out was it starts with the study of. So there's almost this kind of like implicit implication that the statistical engineer, whoever that is not actually doing the statistics or the engineering. They are studying other people who do these things. And I'm just wondering if you can provide your thoughts. I have some thoughts on that, but if you could provide your thoughts on, who is the statistical engineer? What does a statistical engineer do?
I had not thought of it that way, to be honest with you. Well, as I am an engineer and we're problem solvers, so we're applying this, what we have learned through study. So I had not thought of it that way. That is an interesting take on it. As the diagram on the right shows, it's really that bridge between the theory, the strategic, and the operational. And so between theory and practice. And if it's defined as an engineering discipline, then it is applied. It is using that study of thinking methods and tools with the combination of other disciplines. And then to solve important problems are those grand challenges.
Yeah. Yeah, I think I very much agree with that perspective. I think there's room here for both the theory and the application. And admittedly, this quote here, this definition, I think could maybe more aptly say the study and application of systematic
Yeah,
integration,
it's certainly
et cetera,
something
et cetera.
we as the ISEA board need to take into account as we refine and update the handbook.
Yeah, yeah, and I'll also sort of acknowledge and mention that to those in the audience that this is an ongoing process. If you were at our last webinar with Caleb King, and you can watch that recording or look at the slides, they're posted on our website. It sort of acknowledges that these definitions are sort of evolving and always undergoing change. But yeah, I think that the statistical engineer, just like a statistician, there's room for both the theory and the practice, the study of developing new ideas and sort of the more theoretical side, but then also the applied
that
side.
we understand the theory, the concepts, so that we can best apply them.
Right, right.
Not
So
just
I think
study
this,
them.
exactly, exactly. So I think this segues into another question here. What advice would you give to statisticians who don't have engineering or statistical engineering background, but want to incorporate more engineering principles into their work?
I'd say I go to this next slide is work with your peers from those engineering disciplines and, develop partnerships, relationships with them, ask them for how you can learn some of the fundamentals behind their discipline so that you can best help them with better, faster solutions.
Mhm.
Because solving these big problems, as the National Academy of Engineering has recognized, is not a solo discipline. It is a team sport. And I think statistical engineering, with just the very integrative nature of it, is a perfect team player in all of this. So let's build those relationships and build those partnerships.
Yeah. Oh, great. So I got another line of questioning that sort of changes gears a little bit, and it sort of has to do with solutions to these complex and messy problems. And so the first question I'll ask is, or I guess what I want to highlight is with that bakery example that you mentioned,
Yes.
you identified the problem. It seemed that for whatever reason, like the flour, the oil, for various reasons, were not being mixed with the right proportions. There were some target proportion or amount that was required, and you're getting more or less of those, creating either a drier or wetter batch.
Mm-hmm.
So that's, you've identified the problem, but that's different from the solution. And so I wonder if you can identify or sort of discuss translating knowing what the problem is to actually developing a solution to those problems.
Well, in the case of the bakery, once they understood that the control system that metered in those ingredients, primarily flour, because that was the largest quantity that was added to the mixer, and that the loop was not big enough for a single batch of chocolate chip cookies. So they needed to change the logic behind the addition of flour to the mixer and not start adding other ingredients until that had been fully complete. Because once they started adding other things, then the weigh scales get off and the weighing gets disjointed, and then they would end up with too much or too little. And materials didn't get fully incorporated properly because they had different things coming in at times they had not planned for. So it was changing the logic then around the flour loop and the addition of flour.
Mm-hmm.
And for the oil, there was some maintenance type things. They actively engaged their micromotion vendor in a different maintenance routine so that they could ensure or minimize the possibility of air getting into their system. But they recognized then that that was at the root of those two things. And then, well, how can we fix those? Well, they recognized that the controls, the engineering controls that had been put in place to meter flour in did not incorporate the whole context of a batch of that size, and that they needed to go back and revisit that whole logic and then reprogram it, which meant involving the vendor that provided that system to them. So it did involve some additional cost because it had not been taken into account initially. Had that controls engineer understood the context of the mixing process and the size of their batches, maybe it would have been programmed correctly the first time. But they'd missed those middle steps of understanding the context of this manufacturing process and had to go back and now reprogram things based on the learnings. And frankly, I don't think the bakery understood the interaction between all of the ingredients and the size of the batch and the size of the mixer and all of the moving parts to this. It was a complex problem. It had many moving parts to it, and they didn't understand all that till we had the data from the system that we were able to analyze through the Six Sigma methodology to identify those relationships.
Right. So then I guess a follow-up, and maybe could you go to slide 13? So I guess the follow-up question is about sort of sustainability of solutions. The final little piece of this graphic here says identify and deploy final solution. And I think the word final there is, could maybe be deleted, because as your previous graphic, the cyclical one, and even this one, it shows,
So that's an iterative
your next
process.
step from here. Yeah, it's iterative. And, probably we shouldn't regard these things necessarily as final solutions, because they may or may not be sustained. And I wonder if you could just kind of speak
that we will learn some things by testing it, deploying it, and improve that process and improve that solution. And the sustainability, I know the word sustainability in our current language is often refers to environmental sustainability. As an industrial engineer, I view sustainability as that we're able to sustain that solution. In other words, people are able to use it consistently and get consistent results out of it. So we've incorporated the people element into our deployment of that solution.
Yeah. Okay, so now again, changing gears, another line of questioning here, because we have the time. This is, I think, maybe a hard one to answer, but an interesting one nonetheless. With the recent advance and excitement around AI, do you see that playing any kind of a role in helping to solve these kinds of messy problems? Does it help in any way? Does it make it easier in your view?
Yes and no. It is a hard one to answer. I think it all depends on, what data was used to train that AI, and what algorithms were used to do that training. The part that may be overlooked again is this understand the context, the people element of the problem.
Right.
The history, the politics, the personalities, and just using the data and the algorithms may not really create a sustainable solution because of the people that are part of the process. And so yes and no. It may help us analyze the data and get to alternatives and possible solutions, but if we then ignore the people aspect of the problem as we deploy it and even test it or even analyze that result, it may not be very sustainable in the long term.
Yeah, I agree. And I think as with anything with machine learning and these AI sort of advancements, it just brings to the fore how important good statistical practice and appropriate statistical thinking is when using these kinds of things. Okay, so I think we got through all these questions. So I'm just going to thank you once again on behalf of the audience. That was a really inspired talk. And I'll remind everyone in the audience that if you want to dig more deeply into any of this, you can contact Susan. She's got her email there on the screen, or you can read her paper that appeared in the special issue on statistical engineering.
And there are case studies and whatnot if you're a member of ISEA, and if you're not, you should be. It doesn't cost you anything, but you can go to the member-only website and find case studies in the handbook. So it's more than Susan's experience here.
And speaking of sort of other resources and things, please, if you're not already, make sure that you've signed up to be a member of ISEA. It's free. One of the many benefits is that you get access to our monthly newsletter, and so that will allow you to keep up to date with other webinars and initiatives that ISEA has going on. In particular, we have more webinars coming up this year. We don't have specific dates, but I can give you a general overview, and you can read the newsletters for specific dates as they are arising. But we have another webinar that is planned jointly with NBIS. That's going to feature Maria Lanzareth, who is going to be talking about DOE in chemical processes. We also have Jeff Vining coming to talk about some statistical engineering initiatives he's got going on in Brazil. So lots of exciting things happening, both in our webinar series and elsewhere. So make sure to stay on top of these by becoming a member of ISEA. You can simply go to ISEA-Change.org. That's our website, and you can become a member for free if you aren't already. So thanks again, everybody. And thank you, Susan. And we'll see you all again soon.